Hello everyone. In this video, we are going to talk about the connection between free energy and equilibrium. But before we get to that, we're actually going to have a conversation about what we mean when we need to differentiate between delta G when we use the superscript 0, as we can see in this equation right here, and when we have delta G without the superscript 0, as we see in the equation here. So let's talk about this equation. Essentially what this equation is, and we're going to show it to you without going through much of a derivation. We're just going to kind of start from here. In this equation, what we are showing is that the delta G without the superscript 0 is equal to the delta G with it plus RT ln Q. And so let's unpack this a little bit. Essentially what we're saying is the free energy change for a process under any conditions, that's going to be the delta G without the superscript 0, is equal to the delta G under standard state conditions. And you'll remember those, of course, being the temperature of 25 degrees Celsius and 1 atm. And actually, if we're in the solution phase, which we will talk about as we go through in more detail, would be 1 molar. So those are our standard state conditions. So when we have delta G 0, we're talking about those conditions. But if I want to get the delta G for any condition, I start with my standard delta G, and then I add essentially what I like to refer to as a correction term. One where we can manipulate the temperature and we can manipulate the components to Q. Now what is Q here? Q here is the same Q we saw back in the equilibrium unit. Q is the reaction quotient. And that is, of course, the mass action expression, or more commonly thought about the equilibrium expression, where you have the ratio of the products over the reactants. So that's what the Q is all about. And let me talk about this equation in a little bit more detail. The way I like to think about it is that every chemical reaction has a fundamental tendency to be spontaneous or non-spontaneous. And that fundamental tendency, that's what we would call the delta G 0. A combustion reaction has an inherent tendency to be spontaneous. Or let's think about a physical example, that ball rolling down a hill. A ball has a natural tendency to want to roll down a hill. Now, as the experimentalist, there's only so much we can do to influence that natural tendency. Namely, we can do things like adjust the temperature or adjust the pressures or concentrations of the reactants and products involved in the system. There's only so much we can do. So I like to think about this equation in the following way. Delta G 0 is sort of Mother Nature's delta G. There's the inherent tendency of a reaction to be spontaneous or non-spontaneous based on what we get out of the bond energy changes to get, say, a delta H, and based on what we would get out of an entropy change associated with the molecules and the energies going through different arrangements. So there's an inherent free energy change associated with a process, the delta G 0. Meanwhile, delta G without the superscript 0, that's what I like to call the chemist's delta G, because we can come along again and manipulate the temperature a little bit, manipulate pressures or concentration, and based on those experimental manipulations, we would get our experimental or chemist's delta G. And what we're going to find is that there's only so much manipulation we can do. Once we have our sort of Mother Nature's delta G, we can change the temperature, we can change the pressure, and the delta G, the chemist's delta G, is only going to be somewhat different from the delta G 0. There's only so much of an impact our adjustment on experimental conditions can make. All right, so that's how I like to think about the relationship between delta G without the superscript and delta G with the superscript. Mother Nature's inherent free energy change for a process, the free energy change of a process based on the experimental conditions that we chemists could impose on the reaction. Now let's play around with this equation a little bit. And here in question 34, it's asking us, if the reaction gets to equilibrium, what changes can we make to the reaction above? Well, one thing that's going to happen as we go to equilibrium is that the delta G is going to go to 0, okay? So the chemist's delta G, so for the particular temperature, for the particular ratio of products to reactants that we are creating in our system, it's the delta G without the superscript 0 that's going to go to 0. And of course, the letter Q, the reaction quotient, will be replaced with the letter capital K because we're now at equilibrium, okay? So if I get to equilibrium, then I can rewrite this equation. So the delta G is equal to 0, and what that's going to imply then is that the delta G 0 is going to equal minus RT times the natural log of the equilibrium constant. And so this is how we can connect free energy change of a reaction with the equilibrium constant of a reaction. And this connection is going to give us some additional ways to think about the concepts of spontaneity that we get from free energy. Let's take a look at what I mean by that on the next page. All right, so here at the top, we're talking about the connection between free energy change and the equilibrium constant. So it says here, as we know, for spontaneous reaction, delta G 0 is going to be negative, right? We've known that for a number of classes now. And if the reaction is spontaneous, what that means is that it favors products. Therefore, the K value is going to have to be greater than 1. So we have here a different way to think about spontaneity. Right now, we've only been thinking about spontaneity in terms of, does the reaction happen? Well, really, a more accurate way to think about spontaneity is, does the reaction favor products? In terms of a quantitative sense, is K going to be greater than 1? So really, from a chemist's perspective, that's what it means for a reaction to be spontaneous. K is going to be bigger than 1, and the equilibrium is going to favor products. Conversely, if we have a non-spontaneous reaction, then that delta G0 is going to be positive. The K is less than 1, and so the equilibrium favors reactants. Okay, so a non-spontaneous reaction doesn't want to go forward, it wants to stay put as reactants. Now here's an interesting thing, okay? Let's say we have a general reaction, and I'll write something A plus B is in equilibrium with C. And let's say for a moment that the delta G0 here is going to be positive. So we know then that this is non-spontaneous and that the K is going to be some number less than 1. Now, if the reaction is non-spontaneous as written, so in other words, right, this equilibrium, as it goes back and forth, it's going to favor reactants. But what that means then is that it's going to be spontaneous in the reverse direction. So if we were to write this reaction as C going to form A and B, then we would have a negative delta G0 and a K larger than 1. So something that's non-spontaneous, that means it doesn't go in the direction presently written reactants to products. But if you flipped it and wrote the products as the reactants, and the original reactants as products, then it would be spontaneous. Okay, so again, the idea of spontaneity connects with the idea of equilibrium. Okay, there's a lot of overlap here between the ideas. So let's get quantitative with some of this stuff. Let's take a look at number 35 here. We are going to go ahead and calculate the equilibrium constant for the ammonia synthesis reaction, making ammonia from nitrogen and hydrogen gases. Okay, and we've been given the information of the free energy of formation of ammonia is negative 17 kilojoules per mole. All right, so now let's go ahead and calculate the equilibrium constant. To calculate the equilibrium constant, I'm going to take advantage of the relationship we saw on the previous page. The delta G0 is equal to minus RT ln K. So if I want to get K, then I need to get delta G0. So we're going to get delta G0 using a products minus reactants calculation. So that's going to be 2 times the free energy of formation of ammonia, which was just negative 17 kilojoules per mole. And then, of course, nitrogen and hydrogen gases, they're going to go in as zeros in this calculation because we are talking about nitrogen gas and hydrogen gas, which are both the elemental forms of those two materials. So there is no free energy value for those. So the delta G zero here then is going to simply be minus 34 kilojoules. All right, so now I want to go ahead and calculate K. So I want to make sure that I'm careful with my units and I make sure I pick the right value of R. So let's go ahead and start plugging in some numbers. For delta G0, I'm going to put it into joules. So I'm going to write this as negative 34,000 joules. All right, so then that is going to be equal to negative R. The version of R we want to use here is going to be 8.314 because this is joules per mole Kelvin. Okay, so we've got the unit of joules in there. We are at 25 degrees Celsius, so that is 298 Kelvin. And then it's the natural log of K. All right, so you just have to make sure that you can work with your calculator effectively here. And what you're going to find is that the natural log of K is going to eventually be equal to 13.7. And then when you take the exponential of both sides, you're going to see that K is equal to 9 times 10 to the 5th. A note about sig figs. Okay. I had 3 sig figs going into my delta G over here. I've got 4 sig figs, 3 sig figs, so I can report my natural log of K with 3 sig figs, one of which is a decimal point, right? We go to 1 decimal place. That means I can have 1 value here in my K, in my final K answer, because when we go in and out of the log, the number of significant figures we have coming out of the natural log is going to be equal to the number of decimal places that we had in the natural log. Okay, so let's just kind of step back and take a look. Does this make sense? The delta G0 is negative 34 kilojoules, so it's spontaneous. So I ought to get a value of K larger than 1. And not only did I get that, I got a really large value of K. Okay, what you're going to see is that small changes to delta G's can result in large changes in K because of this logarithmic relationship. Okay, so that all fits together nicely. It was spontaneous. We had a negative delta G. We had a K value larger than 1. Let's take a look then at one more problem here. Let's look at number 36. Okay, so in number 36 here, what we're going to do is we're going to go ahead and eventually calculate a delta G for this reaction, given that we are going to be having non-standard pressures for the ingredients of the reaction. So this is going to require us to use that delta G equation that was shown on the previous page. We're going to eventually need to take advantage of the non-standard delta G is equal to the standard delta G0 plus the RT ln(q) term, okay? All right, so let's go ahead and if you looked some numbers up in the appendix of the textbook, all right, we can go ahead and do a products minus reactants calculation to solve for the delta G0. So the free energy of formation of HBr is negative 53. So I'm going to have 2 times negative 53 kilojoules. All right, the free energy of formation of hydrogen, of course, is going to be 0, so that's minus 1 times 0. And then Br2, its standard state, its standard phase is actually a liquid. So as a gas, it's actually going to have a non-zero delta G. Specifically, what it's going to have is a delta G of 3 kilojoules. So I'm going to subtract 1 times 3 kilojoules, again, based on the balancing. All right, so we put all of this together and we're going to get a delta G0 of negative 109 kilojoules. So what we now know is that this reaction is going to be spontaneous under typical standard state conditions. Hydrogen and bromine will want to come together to make hydrogen bromide. Now, what is the value of delta G if we have these non-standard pressures? So this is the negative 109 kilojoules. This is the delta G if all of these pressures were in fact at 1 atm. But now we're going to deviate from that. And as you can see, we're going to deviate quite a bit, right? We're going to have 4 atm, 0.02 atm, 0.2 atm. So we are going to be noticeably far away from standard pressures here. So let's see what that does to the value of delta G. So now we're going to get the chemist's delta G. So delta G is going to be equal to the delta G0, so that's going to be negative 109,000 joules. So I'm going to convert the kilojoules to joules, plus we're still at 25 degrees, so 298 Kelvin. I know we spent a lot of time at 25 degrees. There will be times that you're going to plug something other than 298 into these kinds of questions. And then 8.314, and of course that's joules per mole Kelvin. And this is why I changed my delta G0 from kilojoules to joules. And then this is going to be multiplied by the natural log of the reaction quotient. So again, products over reactants, and we have to make sure that we raise to the power of any balancing coefficient. So for example, the pressure we're going to be using for the HBr is 0.230 atm. So I'm going to take 0.230 atm, and I'm going to square that. And then we're going to divide this by the pressure of the hydrogen, which is 4.26, times the pressure of the Br2, 0.0242. Now, just a reminder here, when you're writing mass action expressions, things like an equilibrium constant, things like a reaction quotient, and you're working in the gas phase, you want to be in ATM units, all right? So we were given ATM, so we don't have to worry about this too much. We're going to put the units into our mass action expression in ATM. Okay, if you go ahead and crunch some numbers here, what you will see now is that the delta G is going to be equal to negative 109,000 joules, and we're going to subtract from this. Everything in the back end of this turns out to be negative, and it's 1,650 joules. And so our final answer here is negative 111,000 joules, better known as negative 111 kilojoules. So, quick comparison here. Here's our delta G under these conditions that we imposed for the new pressure of hydrogen and the new pressure of Br2 and HBr. And compared to when the pressures would have been at 1 atm, we don't have that much of a difference in the delta G values. Now, one of the reasons this is because, and let's take a note real quick here, what have we done? We've actually made the reaction a little bit more spontaneous, okay? It's more negative. Does that make sense? Well, the delta G0 is based on 1, 1, and 1 atm. But now, under the conditions we have, I have noticeably more than 1 atm for the H2. So I've increased the pressure of H2. Think about Le Chatelier's principle. That increase above 1 atm would start to push this to the right. At the same time, I've also dropped the pressure of Br2 quite a bit below 1 atm. So if we think about Le Chatelier's principle again, that dropping of the Br2 would have caused this to shift back in the left direction, back towards reactants. And then the other thing we did is we took the HBr and we dropped it below 1 atm. So that would have a tendency to push the reaction to the right. So we've got two changes here in pressure that would cause the reaction to go to the right. We've got one change that would cause it to go back to the left. So in this tug of war, there's a greater tendency, a little bit more of a greater tendency for this reaction to go to the right, to go in the spontaneous direction as written. And we can see that in the slight increase in the negative value of the delta G. under the conditions we imposed here. The reaction is a little bit more spontaneous, and that makes sense given the kinds of changes we did to the pressures. Okay, so hopefully now you have a slightly better understanding as to when we put the superscript 0 above a thermodynamic function and when we don't. We put it there if we're just relying on standard state conditions. We don't put it there if we're talking about conditions that we chemists, we scientists, we experimentalists can impose on the reaction. And then the other connection we made here is between free energy and equilibrium. All right, if a reaction is spontaneous, the delta G is going to be negative and the K is going to be greater than 1. If the reaction's non-spontaneous, the delta G is going to be positive and the K is going to be less than 1. So we see mathematically how all of that comes together. All right, that is good enough for now. We'll take a look at the rest of the notes at a later time.